In this video, we're going to be taking what we worked on in the last video and putting this information in terms of an energy diagram. So we're going to be relating this to the overall energy, and that's going to be important as well in the future for when we're talking about bonding. So when we're first starting out, we said that we can, for hydrogen as a molecule, we can take the two atomic orbitals and we can combine them. So the atomic orbitals being from each hydrogen atom, we can combine them to make that bonding molecular orbital, which was our in-phase interactions, our constructive interference. We were able to make basically the bond that way. And then we also could combine them out of phase in order to get an anti-bonding orbital. So we showed that in the last video. How does this relate to energy? So for when we're combining them in phase, what's happening when we're making a bonding molecular orbital is it's actually lower in energy. And so how we would show this, this axis is energy. How we would show this is we would show that bonding orbital at a lower energy than either of the two atomic orbitals themselves. So the bonding molecular orbital is actually going to be down here. Let's just redraw what that looks like. So we saw that that one was when we did have that whole orbital basically surrounding those nuclei. So that's going to be our bonding molecular orbital. We saw that we could combine these two atomic orbitals out of phase, and that would give us our antibonding. And so that antibonding, we did say, has a node in it. And so that means that it's actually going to be higher in energy. So we're going to draw a little spot for this up here. The horizontal lines we're drawing, we're going to deal with what's happening with the electrons. So this one up here will be our sigma star or antibonding. And what we saw is it looked like this, where just the bits of the orbital that were kind of on the outsides of those two nuclei, the parts that aren't kind of going to be overlapping when we bring those two nuclei together, those are just going to be what survives. And we do see that, or we did see that we have a node between the two nuclei themselves. So that makes that orbital higher in energy. The fact that we don't have a nice kind of glue between the two nuclei, there's no negatively charged electrons, it's just those two positively charged nuclei. And so that's actually higher in energy, makes that, that whole orbital higher in energy itself. What's going to happen with the electrons? So originally we have one electron coming from one hydrogen atom. So there's one electron in the 1s orbital, one electron in the other hydrogen's 1s orbital. When they come together, they're going to go into the lowest energy orbital, which is this bonding molecular orbital. And that was that usually that line that we show between the two hydrogen atoms that we said there's two electrons. That's a bond. These are in the bonding molecular orbital. And so we can go ahead and put them into that molecular orbital. That's the actual bond of the molecule. So we have kind of our hydrogen atom on one side of this diagram, and on the other is representing the other hydrogen atom, and in the middle of the diagram is representing the hydrogen molecule. So those are the molecular orbitals in that middle section, and the two atomic orbitals on either side. So that bonding molecular orbital, what we've seen from this diagram is that it's actually lowest in energy. And right now we're just dealing with one bonding and one antibonding orbital. Later we'll be dealing with multiple bonding and antibonding orbitals, so it's not always just kind of one and one. It depends on how many orbitals you're actually combining, how many atomic orbitals you're actually combining together. So the bonding molecular orbitals in general are lower in energy than any antibonding molecular orbitals. In this case, we just have the one bonding molecular orbital, which is lowest in energy. When we put electrons into this orbital, it's actually stabilizing. And that holds atoms together. And that makes the bond. So basically, these two electrons right here, they're in this bonding molecular orbital that looks like this. For the anti-bonding molecular orbital, this is still important. So although the electrons aren't in it for the bond, it does become important if we want to actually break bonds, which we will be talking about later in our reactions. So these orbitals, or this particular orbital in this case, is the highest energy. And putting electrons into this orbital is destabilizing. So if electrons are put into that orbital, we're going to force the atoms apart, because the only place that the electrons can go is on the outsides of the nuclei. It can't go in between them. But this is important because this is how we actually break bonds, is we go in and we'll have maybe some species come with its electrons and put them in the orbital, either the side or the side of that orbital, it doesn't really matter. And then what's going to happen is that there's not going to be anything between these two nuclei then holding them together, and so they're going to fly apart, and that's actually going to break the bond when electrons are in this orbital. So and that's another reason why an atom, like, we don't have helium and helium as a bond, because that has two more electrons than hydrogen does. So they each helium atom would start with two electrons. So we'd end up filling up to the antibonding molecular orbital, which would force the atoms apart. And so that's why we don't have He2 as we do have H2. So antibonding orbital is important for breaking bonds, for bonding molecular orbital is important for making bonds. The next videos are going to be talking a little bit more about how more complex molecules come together. So we're going to talk about hybridization, sp3, sp2, and sp hybridization.